Okay, morning class. Start our class now. Okay, so today we will look at the wave equation, the second application. Okay, so this one, okay, after you have learned this one, you can start to do your assignment. Okay, so the wave equation. Okay, this is the wave equation. Okay, so this wave equation usually describes the mechanical waves such as the water wave, sound wave, or seismic waves. So normally the application can be found in electromagnetics, the fluid dynamics, and acoustics. Okay, so now considering there is a string, okay, there is a string where we fix the two endpoints at this point. Okay, a string is fixed here. Then we plug to form the fx. We plug, let's say we plug at this point. We plug the string at this point, we plug it up to this height, and we hold. Okay, we hold. Okay, so when we hold, that means t equals to 0. This is the initial time, initial condition. Okay, this is the initial setup of your string. So your string at t equals to 0 is in this form. So when you release the point, okay, then the string will start to this one, what we call it moves up and down, and the string will form this wave equation, waveform. Okay, the string will form the waveform. Okay, so this one, the solution of the wave equation is uxt. Okay, the uxt. So this u it represents the vertical displacement. Okay, vertical displacement, that means this one. Okay, so at this point P, the vertical displacement is given by u. Okay, so if we want to find the u at this point, that means it represents the displacement. Okay, that means this distance. Okay, at this point, that means this is the distance. Okay, that is the u. So this u, it actually represents the vertical, okay, the vertical displacement of the string from the x-axis. Okay, so at time t, okay, that means this one represents the time, x represents the distance, okay, the point, okay, the point of the string. This is the model. Okay, this is the model of the wave equation. So we have UTT, UXX, and we have these two boundary conditions. Okay, the string has a length of L. Okay, L represent the length of the string, and these two boundary conditions equals to 0. That means, okay, this one is 0. The displacement of the point, okay, from the x is 0. Okay. Then the initial conditions. Initial conditions, that means what is the form of your string at t equals to 0. So from this example, when we plug the string up as to this height and we hold, this means when t equals to 0, fx, okay, this is your fx, initial condition. Okay, so you have to find the equation of these two lines. Okay, the equation of these two lines for your fx. Okay, and there's another one, okay, initial velocity. The ut represents initial velocity, okay, gx. So if you plug and hold, that means initial, okay, we just call it as gx. Okay, this will be given from the question. Okay, so the solution of this model is in this form. Okay, this is the solution where an and bn can be obtained from the Fourier series coefficients. Okay, this an and bn. Okay, but of course, we will derive this solution step by step. Okay, we are not going to just substitute the L, C, and then find an, bn using this directly. Okay, we will form this uxt step by step, just like how you solve for the heat equation. Okay, now we look at the first example. Solve the following wave equation by using method of separation of variables. Okay, so you are given this PDE. The length of the string is 2 pi. Okay, So at the end, both endpoints, the displacement, vertical displacement is 0. That means the two endpoints are fixed on the x-axis. Okay, and this is the initial condition. Okay, initial condition. This is the initial velocity. Okay, UT, initial velocity. Next, by using the first three non-zero terms of the series, meaning that once you have get the uxt, okay, then we will use the first three non-zero terms to find the displacement of this. That means we have to find for the u pi 10. Okay, u pi 10. Okay, so the steps are similar to the heat equation. Okay, so we will find, okay, from this one, from this we will find the representatives of this UTT and UXX. Okay, so UTT is XT double prime, UXX is X double prime T. Okay, so from here, we will separate the variables X and T and let them equals to P. Okay, this is a separation constant. Then from this, we will separate, okay, we will use these two, this one equals to P and this one equals to P to get these two equations. Okay, these two ODE, these two. And from here, from the boundary conditions, okay, from these boundary conditions, you will get these two. Okay, same exactly as the heat equation. Okay, then we will consider the three possible cases for P. Okay, so we will start from the case 1, P equals to 0. Okay, so still we are substituting the P equals to 0 into this first OBE. Okay, when P is 0, we have X double prime equals to 0. So up to this point, it is still same as the heat equation. Okay, so integrate twice, we get the solution of X. We substitute two boundary conditions. We will find that the A and B are both zeros. And then it leads to X equals to 0. And hence your U is 0. Okay, so we will omit this case. Okay, this is same exactly as the heat equation. And for the case 2, okay, this is still same as the heat equation. When P is greater than 0 for the case 2, we will let P equals to lambda square, where lambda is positive. So we will substitute this lambda square into the P, okay, the first OBE. Okay, so from here, characteristic equation, we get this one. When we solve for the M, we get real and distinct roots. So this is the solution for X. So you substitute two boundary conditions. Okay, this is same exactly as the heat equation. So you will find that A, B are 0. So X is 0, U will also be 0. So we omit this case. Okay, same exactly as the heat equation. Now we look at case 3. Case 3, P less than 0. Okay, so up to this point, this is still same as the heat equation. Okay, so we will substitute the negative lambda square into the P. So you will get a plus lambda square. Okay, for the first ODE. So you solve for the characteristic equation, you will find that this is a complex conjugate, and hence you get the solution of X. So when you substitute X, this one, the first boundary condition, A is 0. When you substitute the second boundary conditions, you get this one. Okay, B is not 0, so sine function equals to 0. For a sine function equals to 0, this angle must be equals to n pi. And hence we get lambda. Okay, but this lambda will be lambda n because it contains the n here. Okay, so when lambda is lambda n, okay, back to here, A is 0. We have this as your xn. Okay, lambda n, bn, xn. Okay, then substitute your lambda n, you get this. Okay, so far this is still same as the heat equation. Okay, then this will be different now because for heat equation it is in first order, but now for wave equation this is second order. Okay, so to solve this second order differential equation, we will use the characteristic equation. Okay, characteristic equation. So we solve for the M, you will find that this is complex conjugate. Okay, so alpha is 0, beta is 2 lambda. Okay, so that's why you get this for the solution of T. Okay, this one, okay? From the characteristic equation, okay, you get this one. Okay, since your lambda n is n over 2 just now, okay, then you substitute This will be lambda n, this will be Bn, Cn, Tn. Okay, get this. Then lambda n, you substitute by n over 2. So 2 cancel out with the 2 here. So you get nt. Okay, nt here for the angle. Okay, so this is your Tn. Okay, when you solve, you get Tn because your lambda is lambda n. Okay, so once you get Tn, combined with the xn, you will get un. So this is the xn just now. This is your Tn. Okay, so Bn, Cn, we let it be En. Bn, Dn, we let it be Fn. Okay, the new constant. So this is your un. Okay, so from un to u, okay, from un to u, we just sum up all this term n from 1 up to infinity. Okay, we sum up all this for n from 1 up to infinity. Your un will be u. Okay, so now we will proceed to find for the en and fn, okay, by using the initial condition. Okay, so the initial condition is given by this. Okay, so we apply when t equals to 0, you will get 3 sine x. Like this, when t is 0. So when this t is 0, cos 0 is 1. You have en only. When this t is 0, sine 0 is 0. So this term is gone. That means you have only en sine nx over 2. Okay, because this t is 0, that means cos 0 is 1. This term is gone. So we have en sine nx over 2 in the summation. Okay, and it is equals to this one, 3 sine x. Okay. So now we want to find for the en. So you have 2 choices, okay, because this is a sine function. Okay, since this is a sine function, okay, you can either apply the Fourier sine series or the alternate way, okay, the alternative way, which is we expand this one. Okay, I show you the alternative way. Expand this one. When n is 1, you have e1 sine x over 2. When n is 2, you have e2 sine x. Okay, and so on. Okay, then on the left, you have this 3 sine x. So now we will compare sine x with sine x. That means e2 is 3. The rest of the e are zeros. Okay, only e2 is 3. Okay, if you use the Fourier sine series, okay, you have to integrate, and you will find that your en will be 0, but not for the case of n equals to 2. Okay, not for the case of n equals to 2, and then you have to find separately for the case of n equals to 2, and finally you will get that e2 is 3. But if you use the alternative way, this is much easier. Okay, this is much easier because we just expand this one and we compare the coefficients on the left and on the right. Then we will know that only e2 is 3 and the rest of e are zeros. Okay, so the only possible en for the solution of u is e2 when n is 2. Okay, so that means this one we will when you obtain the en, put it back here. Okay, put it back here. Okay, but since you still have to find for the fn, so we can proceed. Okay, you can choose to proceed to find for the fn first before you substitute your en and fn back into the final solution. Okay, now we proceed to get the fn. Okay, another one. This one. This is your final solution. We have found en, and next we have to find for the fn. Okay, to find for the fn, we have to use the initial velocity. Okay, initial velocity, this one. So to use ut, means that you have to differentiate your u with respect to t. Okay, before you use this one, you have to differentiate this one. Okay, this is your u. You have to differentiate this with respect to t. Okay, so when you differentiate with respect to t, okay, cos you get negative sine nt. So negative n en sine nt. And this one will be n fn cos nt. And this is still the same because this is a constant. That's why you get this. After you differentiate the u with respect to t, you get this. Okay. Then you can apply your initial velocity where t equals to 0. So when t is 0, sine 0 is 0. This is 0. Cos 0 is 1. So you have nfn. Okay, this one, nfn. And this, okay, sine nx over 2. Okay, so on the left, this ut will be 1. Ut will be 1. So from here, we want to find for the nfn. Okay, nfn. So you have to apply the Fourier sine series formula. Okay, so nfn, this one, equals to, okay, this formula, where your L is 2 pi. Okay, your L, the length of the string is 2 pi. So you substitute L by 2 pi, cancel out the pi, you have nx over 2. Nx over 2. L is 2 pi, cancel out the 2, you have 1 over pi. Okay, this one, 1 over pi. So from here, integrate, okay, integrate sine, you get a negative cos with the same function here over n over 2. The over 2, you bring it up. Okay. Then substitute 2 pi into the x. Okay, 2 pi into the x, cancel out the 2, you have n pi, cos n pi. Okay, but you can factorize the negative 2 over n first. Okay, factorize. Here, I just take out the 2 over n. Okay, 2 over n. So you have negative cos n pi minus negative, that's been a plus. 0 into x, cos 0 is 1. Okay, so next we substitute the cos n pi into negative 1 to the power of n. Okay, so this is 1 minus negative 1 to the power of n. So this is your nfn. Okay, this is your nfn. We want only fn. So n move to the right, you have 2 over n squared pi. Okay, followed by this one. Okay, so this is the whole idea on how to get the en and fn. Once you get your fn, substitute back into the final solution. Okay, your fn, okay, your fn is non-zero. Okay, this is different from your en. En is non-zero only when n is equals to 2. So we break this, we write this into 2 different summation. Okay, we break this into 2 different summations. So for en, for the first case, en is non-zero only when n is 2. Okay, so e2 cos 2t, and then sine x, n is 1, so x over n is 2. Sorry, n is 2. 2 over 2 cancel out, so you have sine x. Okay, you have sine x. But for this one, your fn is this one. Okay, so you just substitute your fn to get the solution for this part. Okay, so you can stop your solution here. Okay, this one we have n odd because we know that when n is even, you have 1 minus 1, which is 0. Okay, when n is even, you get 0. That means n will always, to get the non-zero terms, n must be odd. And when n is odd, you have 1 minus negative 1, which is positive 2. Positive 2 times 2, you get 4. Okay, you can take out the over pi, 4 over pi. So you have 1 over n squared. And then sine nt, sine nx over 2. Okay, but you are allowed to stop here. Okay, and according to the questions just now, we have to find for this u pi 10. Okay, u pi 10. So we just substitute the x by pi, t by 10. Okay, t by 10, x by pi. Then goes to this one. This one, we have to use the first 3 non-zero terms. Okay, first 3 non-zero terms according to the questions. So this one, you just substitute when n is 1, n is 3, and n is 5 to get these 3 terms. Okay, then use your calculator to obtain the final solution. Okay, this final solution shows a negative value. A negative values, it means the string is underneath the x-axis. This is negative value. Here, if the point is here, that means there are positive values. Okay, so that we know that the point is the string, the point at the string is located at the above x or below x. Okay. Okay, so this is the wave equation. Okay, so the way to solve a wave equation basically is similar to the heat equation, and it is just different in the case 3. Case 3, when we solve for the part of t, and we have an extra ut, okay, the initial velocity. Okay, so any questions? So far, I just want you to understand the flow. Okay, next we look at another example. Okay, another example. A string is stretched between 2 points and plugged at t equals to 0. Okay, so that means you are given a string of length 4 units. Okay, a string with length of 4 units, and a string is stretched between 2 points at the midpoint. Okay, plug it up, okay, and hold, because your initial condition is given as this. Okay, that means your fx represent the equation of this. Okay, the equation of this. So later you have to find the equations of these 2 lines for this fx. Okay, then if the string is being released initially with 0 velocity, okay, 0 velocity, it means your ut x0 is 0. Okay, 0 velocity. Okay, initial velocity is 0. And your PDE of the wave equation is this one. Okay. Next, we want to determine the subsequent motion of a point P with distance x from the origin at time t. Okay, this sentence means find for the ut. Okay, find for the uxt. Sorry, find for the uxt. Okay, so you have to first find for the fx. Okay, you have to find for this fx because you will use this later. Okay, find for the fx. So this is the equation to get for the line. So you can either use this formula or y equals to mx plus c. Okay, either one to get for this equation. Okay, y equals to 0.005x, represent this. And the second equation, this one, is given by y equals to 0.02 minus 0.005x. Okay, from 0 up to 2 and 2 up to 4, meaning that you have to find these 2. So how to get these 2 lines? Okay, this is given here. Okay, so in the first interval, if you use this formula, okay, the line is in between these 2, 0, 0. Okay, so 0, 0, and at this point, this is 2, 0.01, 2, 0.01. Okay, so use these 2 points to find for the line by using this formula. Okay, so this is your x naught, y naught. Okay, x naught, y naught. And this is your x1, y1. Okay, substitute into the formula, you will get the equation of the line. And the second interval, 2 up to 4, okay, is in between these 2 points, 2, 0.01, and 4, 0. Okay. This point and 4, 0. Okay, so this is, you can choose this as x naught, y naught, x1, y1. Okay, or x naught, y naught, x1, y1, doesn't matter. Okay, as long as one is x naught, y naught, another one is x1, y1. Then you substitute into the formula, then you will get this. Okay, so now you have found the fx. Okay, you found only the function of fx. Okay, then form the model. Okay, form the model. This is your PDE. This is your boundary conditions. Okay, starting point 0, ending point 4. They are both equals to 0. And the initial velocity is 0, okay, given by the sentence. Initially with 0 velocity. UTX0 is 0. And UX0, this is the initial condition, is given by Fx, and you have found that Fx is this one. Okay, so once you have the complete model, you can proceed to solve for the wave equation. So from this, find for the representative. Okay, UTT, UXX, then you get this. Separate the variables and obtain the two ODEs. And from the given boundary conditions, you get these two. Okay, now we have to consider 3 possible cases for P. But the first 2 cases are similar, okay, to the previous example. Okay, so we go straight to the third case. Okay, third case, which is P less than 0. Okay, so when P less than 0, we will let P be negative lambda squared. Okay, so we substitute P by negative lambda squared into the 2 ODEs, so we will get this 2. Okay, so we solve for this one first. You will get this. Because of the complex conjugate, you get this. Okay, then substitute the first boundary conditions. You will find that A is 0. And from the second boundary conditions, you will get this equation. But B is not 0, so sine function equals to 0. For sine function equals to 0, this 4 lambda must be n pi. Then you can get your lambda. Lambda is n pi over 4. Okay, but because of this n, your lambda will be lambda n. Okay, so you have xn, an, bn, lambda n, lambda n. But because of a is 0, so this term is gone. We have only this for your x. So xn, bn, sine lambda nx. Then you just substitute your lambda n into here to get this n pi x over 4. Okay, this one has been repeated many times, so I just go through like this. Okay, next we look at the second ODE. So we solve for the second ODE through the characteristic equation. Okay, then because of the complex conjugate, we get this. Okay, so lambda n, substitute your lambda n into this lambda. So we have Tn, Cn, lambda n, Dn, lambda n. Okay, so after the substitution, you get this as your Tn. So combine your Tn with the xn just now, you will get your un. Okay, Vn, Cn is En. Vn, Dn is Fn. Okay, so once you get your un, we want to get u. So this whole term will give a summation n equals to 1 up to infinity, then un will be u. Okay, so next we have to find for the En and Fn. Okay, we find for the En first. We will apply the initial condition. Okay, so what's happened when t equals to 0? It's 1, t is 0. So when t is 0, cos 0 is 1. So this is 1. You have only En. Sine 0 is 0. This term is gone. Okay, this one, there's no t, so we still have sine and x, n pi x over 4. That means En sine n pi x over 4. This one, okay, equals to this one fx. Okay, now since your fx is a piecewise function, we have different function in different intervals. Okay, so meaning that when it comes to the integration, okay, we have to break this into 2 parts. Okay, because your fx is different in different interval. Okay, and this is not a sine function. This is not a sine function where we can't get to expand and compare the coefficients. So that's why we have to use the Fourier sine series. Okay, because of this is sine function. Okay. So we use this formula to get for En. So this one and this one, we solve using tabular method. Then you will get this line. Substitute the 2 and 0, 4 and 2. You will get this line. Okay, you will get this line. Simplify. Then you will get this. Okay, this is what you have learned in chapter 4. Okay. And you get this one, this as your EN. Okay, once you get your EN, okay, look again at your final solution. You have get your EN. We want to find for the FN. So to get FN, we have to use the initial velocity. The initial velocity is UT. So we have to differentiate this with respect to T. Okay. So when you differentiate this one with respect to T, cos, you will get negative sign. Okay, negative sign 5n pi T over 2 over 5n pi, the over 2, you bring it up. You will get this. Oh, sorry, differentiate. This is differentiate, not integrate. Okay. Once again, this one. Differentiate cos, we get negative sign of this function, then 5n pi over 2. Okay, differentiation. And this one, sine, you will get cos function, and then 5n pi over 2. We put it here. Okay, this is a constant. Okay, this is just a constant. That's why we get this one. Okay, this is your UT. And finally, we apply the initial velocity when t equals to 0. This whole thing equals to 0. Equals to 0. So this one, when t is 0, sine 0 is 0. This term is gone. When t is 0, cos 0 is 1. So you have this. This one multiplied to this sine function. Okay, so now we want to find for Fn. Okay, that means the whole function, this whole function, we put it here, equals to, we have to use the Fourier sine series. Okay, because of the sine function, we use the Fourier sine series. Okay, L is 4. Okay, the length of the string just now is 4. So we substitute L by 4. And your Fx is 0. Fx is 0. So 0 multiplied sine function is 0. For this definite integral, okay, this will get 0. Okay, it will give you 0. So 0 times 1 over 2 is still 0. And hence your Fn equals to 0. Okay, substitute your En and Fn into the UXT. And this will be your final solution. Okay, this one is similar to the your assignment question. Okay, where you have to find for your Fx. Okay, your Fx. Okay, now we look at the exercise so that you are clearer with all of the steps. Consider simple. We do not need to use the Fourier sine series later. Okay, we can expand and compare the coefficients of the both sides. So now we write down the representative of this PDE. Okay, UTT. Because of this assumption, your UTP can be written as xt double prime. Okay, UXX is x double prime t. So write this, separate this, then obtain the two ODEs. Okay, whoever sign for your attendance. So this is similar to the field equation. Okay. So for the first case and second case, it is same exactly as the heat equation. So we look at the case 3 directly. So when we substitute the negative lambda square into this P, we have a plus. In the two characteristic equation, then apply the two boundary conditions to get A and B. Once you have get your xn, we have to find for the tn. Okay, t. This is the same as the first OBE. You get the plus minus lambda I for the m. Okay. Once you get your XUXT, apply the initial condition. Okay, apply when t equals to 0 to the UFT. Okay, when t is 0, plus 0 is 1. Sine 0 is 0. Then you still have a sine function. Okay, since the left-hand side, there are sine functions, so we just expand this one. Okay, she find for the En. When n is 1, plus when n is 2. Okay, so from here, we know that E1 is 4. E2 is -3. E3 and so on. They're all 0. Okay, once you have obtained the En, you can proceed to apply the initial velocity to find for the Fn. But before you apply, you have to differentiate this u with respect to t. Okay, differentiate all function this with respect to t. So cos, we get a negative sign, negative n en sign and t. And this sign, we get a cos function, and this n and cos and t. Sin nx is just a constant. Then you can apply the initial velocity to get an fn. Any questions so far? Okay, once you have differentiate your u with respect to t, substitute the initial velocity when t equals to 0. When t is 0, sine 0 is 0, cos 0 is 1. So you have n sine nx. Okay, L is pi. L is pi. So for the final solution, UST we break it into two because EN is not zero only when n is 1 and 2. The rest are 0. And Fn is 1. One is 4. Two is -3. Okay, this one, when n is even, you will get 0. Okay, when n is even, you will get 0. That's why the final answer given in the slide is n odd. Okay, but you can maintain. Okay, you can remain this as your final answer. Any questions? Okay, now we look at question number 2. A stretched string of length 20 cm, okay, 20 cm of the length is set oscillating by displacing its midpoint. Okay, its midpoint a distance 1 cm from its rest position. Okay, 1 cm. So there is a string fixed at these two endpoints, but at the midpoint, it is plucked from the positions, okay, from the rest position, and released with 0 initial velocity. Okay, 0 initial velocity. Zero initial velocity. So this is your initial condition. Your fx is your initial condition. You have to find for the fx first. Okay, this is the midpoint. Okay, to get the equation, okay, there are two equations here, two different equations in two different intervals. So find for the interval, the first interval, 0 up to 10. Okay, you have 2 points. Okay, the first point is 0, 0. And the second point is 10, 1. So you use this formula, y minus y naught equals to y1 minus y naught, x1 minus x naught, x minus x naught. Okay, use this formula to find for the first equation. X naught, y naught, x1, y1. Okay, so the first equation is y equals to 0.1x. For the second part, we have 10(1) is the point, and the point is 20, 0. For the second interval, I choose this as x naught, y naught, x1, y1. Okay, because y naught is 0. Okay, if your y naught is 0, it would be simpler. Okay, y1 minus y naught, x1 minus x naught. Okay, once you have get your fx, you can start to find the representative of this UTT and UXX. Okay, so same goes to the first question. We skip the first two cases. Once you have get your uxt, apply the initial condition. When t is 0, okay, when t is 0, you have en sine mx over 20. But your fx is in the form of a piecewise function. And there are not sine functions, so you have to use the Fourier sine series, okay, and break the integration into 2 to get the en. Okay, solve the two integral by tabular method.
Now we look at the substitution. 10 into here and here. Okay. So this will be n pi over 2. On it. This one will be n pi over 2 as well. It's 0 into x plus 0 is 1. But this one, when x is 0, this is 0. Okay, sine 0 is also 0. For the second part, 20 into this x, you get a 2. 2 minus 2 is 0. And 20 into this x, you cancel out the 20, sine and pi is also 0. And into this x, you get 2 minus 1. 1 times negative 20. Cos and pi over 2. Minus sine also and pi over 2. Okay, these two, one is minus, one is plus. Wrong. Minus, minus, we get a plus, 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 so 18. Cancel out with a 10. Okay, now we have get the Fn, so we will proceed to find for the Fn. But before the Fn, you have to differentiate u with respect to t.
one for the UT first. Okay, differentiate this one respect this one and 10 are constant.
I guess.
Even the initial velocity as 0. When you substitute t equals to 0, find 0 is 0. This is false. Cos 0 is 1. Then find the sine function. Okay, so this one, this constant equals to this formula. We have to use this formula to find for the constant. Okay, the L is 20. Then this is 0, that's means integration of the definite integral, you get 0. And hence your Fn is also 0.
Thank you.
Okay, now substitute your En and Fn back into your UXT. Fn is 0. You still have this cost. This is your En, and then cos. Then sine. Okay, any questions? Working is long, but actually there are repeating. Okay. Now, when I call your name, hands up, huh? Call. Hồng Yêu Chen. Đâu Chuyên thấy. Afik Amnan. Ahmad Anna. Ahmad Hazin. Dayang. Muhammad Sufi. Amirul Ashraf. Faiz Syami. Nurul Naima. Ong Keng Thiam. Dugan. Dugan Tiran. Teng Yong Ying. Ong Xuân Hao. Ahmad Faiz. Kim Jung-jae, Chung Ai, Darius B. Trump, Davendran, Subendiran, Karan, Hong Wai-in, Lukman Hakim, Arif Zulkarnain, Usman Hasib, Nazri, Safwan, Shahrul Azim, Zaki, Miljin Wei, Fakri, Sri Tepan, Tina, Binoff. Okay. So today we end our class. We end our class here, and we will continue on first day.